So you're introducing.
Oh, okay. Yeah. So this is a project that we are working on. We are working on the face and eye detection and tracking. Like our group members is James, this Adrien, and Patrick.
Our first, my project is determining eye detection and color images based on chromaticity and geometric constraints. Adrien is using eye detection on horizontal and vertical identifiers. He's also doing face detection using color information and face detection using local hue, saturation, and histograms. And finally, Patrick is working on classification of eyes using phase classifier. Again, my research is based on eye detection and color images based on chromaticity of the image and geometric constraints. Based on the papers I've read, working to find the eyes and mouth points for a color image. The color image is transformed into the YCBCR color space, and it's broken down into the YCBCR components, where Y is the luminance or the brightness of the image. The CB is the blue difference chroma, where it's blue minus the brightness, and CR is the red difference chroma, where it's red minus the brightness. The final product is a mouth map and eye map containing possible eye points and mouth points. The eye map is composed of two sub-eye maps, where based on high CB values and low CR values around the eye. The first eye map C takes the CB component, squares it, takes the inverse or the negative of the CR component, squares it, and adds it finally to the CB divided by CR component. The 1/3 is to ensure that the value is between 0 and 1. The second eye map takes the luminance component, puts it through a dilation operation with a ball mask or ball structuring element, and divides it by, again, the luminance component with a dilation operation. The +1 is to ensure there's no division by 0. After both these IMAP C and IMAP Bell have been found, they can be multiplied together to form the complete IMAP. The mouth map is based on strong red and weak blue components around the mouth. The eta component here is just the average of the pixel values for the CR squared value, and the average divided by the average of the CR divided by CB value. This is put into the equation for CR divided by CB, subtracted from the CR squared value. That value is squared and multiplied by, again, by the CR squared value. After going through a smoothing function to smooth the high points, both maps are plotted for the high points. This is a picture I got from my girlfriend. You can see the IMAP image here, where each red dot corresponds to a high point in the IMAP, and then the blue dots here is each high point in the mouth map. After determining potential eye and mouth points, geometry tests can be performed on the eye-mouth combinations to try to eliminate possible face images. There's a test to measure the angle between the eyes and the mouth. There's a test to compare the two eye-to-mouth distances. And there's finally a test to compare the eye-to-eye distance and the eye-to-mouth distances. For example, if this is a triangle comparing one eye, the second eye, and the mouth, the angle between the eye theta 1 and theta 2 should be between 54 and 78 degrees. If it's between those values, then it passes the test and moves on. The second test compares the right eye to mouth distance with the left eye to mouth distance. If that ratio is between 1.08 and 0.92, or plus or minus 8%, it will pass the test. And finally, the third test is to compare the eye-to-eye distance with each one of the eye-to-mouth distances. If it's between 65% and 100%, then it will pass the test. If an image passes all three tests, the triangle will be plotted on the image to show a potential face for the image. using the previous image, if I used only the mouth, the correct mouth point, and all eye points, it came up with 3 possible face images, including the correct one. There's, out of 14 eye points for this image, there's a total of 91 possible combinations. It finds 3 that pass all 3 tests and takes about 0.3 seconds. Now if I use all 16 mouth points with all 14 eye points, there are 1,345 possible combinations. It finds 19 possible face matches. It's kind of hard to tell with all of them overlapping one another, but there's one that takes about 1.6 seconds. Now the problems with the research and the code that I have is there's quite a few mouth and eye points. 14 to 16 doesn't seem like a lot, but if depending on the image, it could be more, it could be less. But we're trying to eliminate a lot of those eyes and mouth points. The geometry helps, but even with geometry, for only one face, it finds 3 possible face images, and then that's only using the correct mouth point. If I use every point, it finds a total of 19. So that's a little more than you want to get. Hopefully, with probabilities, trying to find the probability that one point is an eye, finding a probability that point is a face or point is a mouth, we can eliminate some of those extra points or extra face combinations. We might also use extra geometry tests. For example, if you're assuming a person is working at the computer, he's not going to be turning sideways with his face or upside down, so you can assume that both eye points, Y value, are higher than the mouth point. So if there's a mouth point that has a low Y value between the face or the mouth and the other eye, then you can eliminate that combination because they'd be looking like this or upside down, which they probably wouldn't be working at a computer or looking through a webcam. And then we can also use partner research to try to eliminate background where we can just cut the face. If we can just cut the face, then a lot of these points around here and here can be eliminated. And my research is based on these 2 references, eye detection in face images and face detection in color images. The equations came from these papers, but all code and all results are my own.
All right. I'm going to talk a little bit about eye detection using horizontal and vertical identifiers. You can see the paper which I use as a reference. Basically, this is the idea behind this concept. You will get a frame of your face. Hopefully, there will be no hair in the frame, especially for people who have dark hair. Then you'll invert the image, and you'll see that as you invert the image, the eyes will be the brightest value, hopefully. Also the mouth and the eyebrows in some cases. As you invert the image, you will identify the maximum values in every horizontal row. For example, you will search through this row looking for the maximum, then this one, and so on. You'll repeat the same vertically, and then you'll match them. You'll match the horizontal maximums and vertical maximums that you find. After that, you will need to filter those vectors because they will give you more than one maximum. They'll give you plenty of maximums. But you only need 2 of them, actually. 2 vertical ones and 1 horizontal one. This method also assumes that the face is straight, not that the face is tilted, because we're doing this horizontally and vertically. So we have to set up some thresholds, and if the maximums go past the thresholds, we'll set those up as coordinates. This is a very exaggerated X and Y coordinate. This actually doesn't really look like this. I exaggerated it for this presentation. This is the vectors of maximums, the verticals and the horizontal ones. It's actually, if we hadn't filtered it, it would look something like this. It would have a lot of peaks. And basically this is one of the problems with it. The eyebrows sometimes can have a larger maximum than the eyes. So if you put a threshold, it might pick up both of them. Also, if you have an open mouth, that's the 3rd horizontal maximum. If you have a mustache, that's that's another horizontal maximum. This can be actually eliminated, the eyebrows, using geometry, because simply if you know that if you have one on top of the other, you'll take the one in the bottom as the eyes. The problems with this method is, first of all, the eyebrows are often detected. Second of all, the mouth can be a horizontal maximum. The mustache, hair in the face can also be considered as a maximum. Eyeglasses, with eyeglasses, it depends on them. With some of them, it will actually work. With some others, it will not. There's also another problem that I can't really explain why it happens, but sometimes it picks up a maximum, not in the very pupil of the eye, but in the corner of the eye, in addition to the pupil. So it will pick two eyes and a third one. It also always happens in the side where the light is coming from. I don't really know about that one. The paper which I use as a reference mentioned that the eyebrows will always have a value larger than the eyes. From my code, it's different. Although it's not I use my own code, of course, not the very code that they implemented the paper with, but this is what I got as a result. And as I mentioned, some of these problems can be solved using geometry. Now, the second thing I tried was detecting a face using just the color information. So we would go in a frame captured by the webcam, go in pixel by pixel, and we'd actually have some color information that we would think the face would use. And we'll calculate the Euclidean distance from that pixel to the color of an actual face. And if the Euclidean distance is smaller than a certain threshold that we'll choose, it will detect that as a face. This is, for example, like a best case scenario working right there. We, of course, after we detect that each pixel belongs to a face, we'll put some filtering so we won't get just like a pixel spotted around all the face, but we'll actually get a good circle on top of every filter, so we'll get the face without, for example, because the eyes are not the color of the face. The eyes are black or green or blue or whatever, and the face will be of a different color many times. So if we didn't filter it, the eyes would be a black spot in here. The problem with this method is that if you set very specific thresholds under one light condition, you move to another one, and you'll get nothing. It will be basically, you can see this. This is, for example, the first picture I took, I think it was under light of day. This was in the 7th floor of the electrical engineering building with a fluorescent light. And you'll see that it will pick up some points in the face, but also pick up a bunch of things everywhere else. So you can't really go very specific with the thresholds just based on color detection. This is, for example, a worst case scenario. I set up the thresholds very specifically under a different light condition, and you'll see these are the points that it picked up. It picked up many points outside the face. It picked up some points around here, around the eye area. And after filtering, you can see that it basically didn't do much. And this problem got solved a little bit using HSV instead of RGB. It was a little bit more consistent, but we still had to do a little bit more. We tried, since we're using a webcam, we tried subtracting the previous frame, assuming that the person will have a slight movement. And it also made it a little bit better, but then it added an additional threshold because we couldn't make the subtraction equal to 0. It was too absolute. We had to make another Euclidean distance comparison to the previous frame and see if it was over another threshold. If it was too small Euclidean distance, we assume, yeah, it's the same pixel as the last time, pretty much. There was another problem with that. There was addition that when you take a webcam, some pixels will just kind of change. They will not be accurate, so we had to do an opening and closing operation to get rid of that. Now, this is the last one I was working in, which is face detection using local hue and saturation histograms. It's basically the same thing. Grab a frame from the camera, and what we'll do is we'll divide the frame in very large portions, a little bit overlapped, but we'll analyze big frames. And then, as our analysis goes on, we'll analyze smaller frames out of the one that matches the best the face. That's to save, obviously, processing time. We'll divide a big frame in, for example, I don't know, 12 smaller frames. And out of those, the one that matches the best, we'll divide it at a time in a bunch of smaller frames, and so on. Once we acquire the histogram, we will calculate the similarity between the histogram and the histogram of a sample face. Of course, this requires face. It requires some color information to process. And then we'll analyze it. This is basically what we'll do to compare the two histograms. We'll sum the matrix that results from taking the square root of the multiplication of a sample histogram and the histogram of the portion of the frame that we're currently analyzing, the one that returns the maximum value. We'll assume that's the square in which the frame is. As we're looking for a maximum, though, it will always detect the face even if there's no person inside there. It will detect somewhere that there's a face. Okay, this is originally we're trying to use RNG histograms for red and green for the face. The problem is that, for example, if you have a darker skin tone, this is the histogram of a room with a person facing the camera. And this is the histogram of just that person's face. As you can see, it's basically under this, so we can't use really any function to separate it. If you have a darker skin tone, this will actually be around here. And it's easier to separate. If you use HS, hue and saturation, you can see this is the room, and this is the person's face. So it's a little bit different, and kind of we can take the comparison of a frame to this, and that will give us a better result. In our program, we're actually using a smaller resolution or histogram. This is a 255 division. This is just a 50 division. But you can see that this is a sample of a face in this histogram. This is a sample of just a skin tone, a small skin tone. A small square of the face just containing the skin information. The problem with this is that we have to do many for loops. It's low. Also requires a sample of the face and the skin. It also deletes some divisions inside the face. This can be solved with filtering, and it also keeps a few divisions outside the face, which can be solved by what we did with the color detection, or deleting this frame from the previous frame and keeping the difference. So you can see this is a full frame. I run the program, I look for the division that match the face the most, which is this one. And after that, it analyzed the face in a smaller division, and it kept that. And we hope that we can combine this with James' code and eliminate a bunch of those points outside the face, and make his program work a little bit better.
Okay, my part of the whole project is to build a classifier. The classifier is basically like going to like identify the facial features, like the eye, the mouth, and all other features on the face. Okay, so my part of the program, my part of this project is to get a data from Adrian and James and train my classifier to recognize these facial features. Okay, so this is like an example. This is an example of a maximum likelihood classifier for a left eye. Okay, when you put like a data, when you put a data into this classifier, the probability that, like I'm using the probability density function. The probability that is a left eye, it's a half of like the whole data. After the adjusted data, this is my adjusted data. My adjusted data is basically like the data, the original data, where I subtracted. So when you subtract the mean of the original data from the original data, then you take a transpose of it, and you multiply it by the covariance matrix times the same adjusted data. Okay. So like in my classifier, it's like there are two different ways that I can build my classifier. Yeah, I can like there's a function in MATLAB called a PCA. So my PCA that does the principal component analysis. The PCA is basically like guess my data, original data, and just like compress my original data, and make the dimensionality like simple, like small, to compare with a new set of data. So there is a whole process of principal component analysis. So there is a whole process of a PCA. To use your PCA in the MATLAB, you just get like a set of data. Like get a set of data like a set of data and transport into like a vector, like a data of like n by m by n. And first of all, you have to compute the mean of the whole vector. After that, after you get the mean, you subtract the mean of the vector from the original data to get an adjusted data. After you get this adjusted data, you find a covariance matrix. You find a covariance matrix of your data. After you find the covariance matrix, you can actually, like, there's a function in MATLAB that's like I of the covariance matrix. So you just put like I of the covariance matrix is going to give you the eigenvectors and the eigenvalues of the covariance matrix. So to get this new set of data, you are going to use this your eigenvector times the original data. And when you multiply the original data by the eigenvector, the new eigenvector that you find, it's going to reduce the dimensionality. And it's going to make your new data vary less with each other. So like over here, I'm trying to like illustrate the whole process of a PCA analysis. There's like a normal data, and there's my final data. After you pass this original data through the whole PC analysis, there's the data that you're going to get. So there's a graph of my original data, and there's a graph of my final data. And there's a code that I'm working on right now. There's a code that I so far already got in MATLAB. I get my set of data, go through the whole process of PCA. And there's a continue. And there's a reference of the paper that I'm using to build my whole classifier. Okay. Any questions?
Yes.
Yes.
A question for you, James. Have you considered using lengths along with angles to help determine the eyes to the mouth?
Yes, two of those tests are based on lengths or distance between the eyes. The lengths of the top of the triangle, and both other two sides as well.
The other, okay. I was just curious.
Yes, Dr.
Do you have any overall picture on this project, like how when three of you put all your work together, eventually what deliverable you will provide?
Hopefully we can deliver, if it's a video, they can keep track of the eye and the mouth, or to determine, okay, that's a face, you know, we can follow that face. One of the big things to work on was for those that are disabled or handicapped, they can be able to use their eyes to control a mouse for a computer. So we want to be able to know where those eyes are. Those are their eyes, to be able to take that information, where they're looking at, you know, how those eyes change, to be able to let them control a mouse or something like that.
Okay. Can I follow up on that question? Like my part of the project is to build a classifier. So like after I get this set of data from Adrian and James, like I'm going to compare like a whole feature, like a whole face to my classifier. So you know, like after like when you compare this whole face to my classifier, the classifier is going to identify like, okay, like this feature is like is similar to this set of classifier. So that's my part of the project I'm doing.
I have a time issue. I mean, you said the ultimate purpose is basically for a person that can't move his hands, maybe to use the eyes as a mouse.
Correct.
Eyes as a mouse. So it has to be very fast. And if you're pre-computing all the, taking principal component analysis, and you're doing all these computations, I can't believe that it's possible to follow the eyes.
Yes, I mean, there's a lot of work still to be done to be able to keep it fast enough.
The idea is to use the histogram analysis that I'm using to speed up his process. I tell you that I took big chunks of the picture at first, and they'll detect the one that's closest to a face. that part of the code is actually very fast. The smaller one is the one when I start taking smaller points. But if I just feed that square to him, he'll have a lot less points to analyze, and his code will be much faster. We're also receiving our input from a webcam, so we'll have about 15 frames per second. We have 1/15 seconds of time to process a frame.
Oh, well, I just want, well, you said you were going to compute the facial area so that he can eliminate some of the points, but I can't, like just what Dr. Bush was saying, I don't think it's going to be fast enough, so why don't you just make the sampling process of yours slower than his so that it'll just eliminate some of it, you know what I'm saying? Like, all right, his will be very fast, but yours will be a little bit slower, so it'll get a general region of where the eyes and mouth are.
That's the idea. Yeah, get a general region where the face is, and then he will get.
Okay. Okay, I see.
Yeah.
Patrick, and I think it was also in the outlays slide. Go back to where you talk about base. Okay, no, one more.
Okay.
Where you were, there. BAYS, what's wrong?
BAYS, the base classifier.
Base classifier.
Yeah, it's base with an E.
Oh.
And there's no Mr. Bay, it's Mr. It's base classifier with an E, and you have that problem both places, so you must have read it enough to know that that's wrong.
I'll mark this on your slide.
Any other questions? Dr. B, you sure you don't have another one? Just kind of haven't smirked it. I have another one, but I have to go early.
We gotta go.
No? All right. Thank you.